Hello, ladies and gentlemen. I hope you're as ready as I am for question number 24 on the 2003 Pascal paper. Question 24, an artist wants to completely cover a rectangle with identically sized squares, which don't overlap and do not extend beyond the edges of the rectangle. Okay, so you're sort of like tiling a floor or something. You can't go over the area because you'd run into a wall, and you can't overlap tiles or they won't all stick in place and you'll stub your toe and everything. Okay, so that's the idea here. But we're told all the squares are going to be the same, but we aren't told what size they are, so that might be something we need to work out. If the rectangle is 60.5 centimeters long and 47 2/3 centimeters wide, what is the minimum number of squares required? Ooh, okay. Minimum number of squares required. Well, let's look at sort of a simpler example. Suppose I were looking at something and it was 2 by 3.5. Okay. So what sort of tiles could I have? I could easily get 2 tiles that are 1 by 1 here. If I keep going with these 1 by 1 tiles, I'll be fine up until I try and lay my last 1 by 1 tile. It's going to overlap. We're not allowed to have sort of overhang over the edge. So whole numbers aren't going to work here. You can't, because we've got this 3/2 here, we can't do it with whole numbers. They're squares, so I can't have, say, 1 by 1/2 and have it all work out. And I think that's part of the key to this question, because we've got that 60.5 centimeters is one of the dimensions. So that means that there's no way we could have 1 centimeter by 1 centimeter squares. Okay, it just wouldn't work out. All right, so that's something to consider. So in this case, we would need to use halves. Half, a half, and I'd get 7 of them over here, and 4 of them going this way, and that would be 7 by 4, which would be 28. So 28 half by a half squares work. Okay, so that's the sort of thing we need to work out, these half by halves. Now, is this the best I could do? That's a good question. Is this the best I could do? So if I have, obviously I have to sort of have a base of a half. I could have smallers. I could have a quarter. I could have quarters in there, certainly. Or eighths or something. Or sixths would work out just fine. And have 3 of them in the space here. But we want the minimum number. So just because 28 half by a half squares do work, doesn't mean that that's the best answer. Maybe 3/2 by 3/2 might work. Okay? It doesn't. In this case, just I can sort of plot it out in my mind. But that's something we need to be aware of. Okay? But first, let's at least get some squares that work. Okay? If we get some squares that work, we might be able to better understand what's going on here. So what were the dimensions we were given? 60.5 and 47 2/3. Ooh, okay, that 2/3. That's going to mean that we can't just use halves. So 60.5, 47 2/3. If I just use a halves, I'm going to get overlap with my 47 2/3. A half doesn't evenly divide by that. So if we use n by n squares, we need 47 2/3 divided into n's to be even. We need to get a whole number there. Otherwise, we'll have overhang, or we'll need to overlap, or sort of have something like that. Same thing with the 60. So we'll need 60.5 over n to be integers, whole numbers. Okay? So I have no idea what n is, but it's going to have to be a fraction at least. Probably, I mean, it can't be a whole number, for the same reason it couldn't be a whole number over here with the 2 and by 3.5. I think something like a sixth by a sixth would work, for example. First thing I'm going to do is actually, I don't like writing this 60.5, so I'm going to convert these just into proper fractions. Actually, I think they're called improper fractions, but I don't like having this mixed nonsense. So 47 times 3 is 141, and if we add 2, we get 143. So we need that, and 60.5. 60 multiplied by 2 is 120, so we'll have 121 over 2 over n. So we'll need those to be integers. That's what we're looking for here. And if we get the biggest n that we can, we'll have the smallest integers, and then we'll be able to figure out, oh, it's a, if we tile it this way, it's a what by what, and then multiply it out, and that'll tell us how many tiles we need. Just like having a 4 by 7 over here told us 28. Half by half squares would work. Okay. So now I sort of need to work out the greatest common fraction divisor here. It can't be an integer, it's got to be a fraction. Well, a 6 works out really well. So how about, in fact, yeah, that would be a good idea. How about we work out let's change that to 286 over 6, and I'm going to let n be m over 6. And 121, that's 363 by 6 over m by 6. All I've done is I've made it so all these fractions are over 6. Okay. Well, when I do that, the 6's cancel out. I've got 286 over m, and I've got 363 over m. So to have the biggest squares, m must be the biggest divisor of 363 and 286. Notice that there's nothing wrong with m still being another fraction, but fractions will... I think we should only get integers here. So some of you might be worried, why did you... I mean, obviously the 6 works out because you have the 2 and the 3 there, but how do you know n should be written as m over 6? The truth is I don't. I'm prepared for m to be another fraction, so long as these become integers still. Okay? But I want them to be sort of the smallest integers I can make them. So, what can I do here? Well, it might be a good idea to, if you're trying to find the biggest divisor, it's always a good idea to write it out as its prime factorization. So break it down into primes. So I know we've got a 2 here. It's easier just to do this by calculator. 286, you divide by 2, you get 143, so that should be 13 times 11. So 2 times 11 times 13. 363 here, that'll be 3 times 121, that's 11 squared. So it looks like both of these just have a common factor of 11. Now, how can I rule out there not being a bigger fraction for m to be? Because what I'm worried is that maybe 23 over 2 equals m does better, or something like that. I think I've got it. So I've got these guys as common fractions. Let's not write n as m over 6. Let's write it as p over q. That way it's just a generic fraction. Okay, and so this one will be, we've got a q up here. And we get 6p here, we get 6p here, and q here. Okay, and these have to be integers. I think that's the best way to go about doing it. I'm pretty sure the answer will be 11 over 6, but I'm a pure mathematician. I like to be rigorous. If you're satisfied with 11 over 6, by all means, go for it. So to have the biggest squares, we need so to have the least squares used, we need the squares to take up as much space as possible. Okay. If we want them to take up as much space as possible, n needs to be as big a fraction as possible. I'll come back to that prime decomposition in a moment. Okay, so we need n to be as big a fraction as possible. How do we make fractions big? P needs to be large, Q needs to be small. Okay. So, first I need 6 to divide 286 by multiplied by Q, and I need 6 to divide 363 times Q. Okay, well, 286Q is just 2 times 11 times 13 times Q. Well, if 6 is going to divide that, 6 is equal to 2 times 3. So we know that 3 needs to divide Q, because there's no 3 anywhere else in here. By the same token, 363Q is 3 times 11 squared times Q. In order for 6 to divide this, I need a factor of 2 somewhere. So 2 has to divide Q. Taking Q to be small, it shouldn't have any extra factors lying around. We need 6 to divide Q, so let's say Q equals 6. If you're not satisfied by saying Q equals 6, you can at least agree that 6 is a factor of Q. So why not write Q as 6K if you want to be super exact? But I'd say there's nothing wrong with saying Q is equal to 6 at this point. Q needs to be small, P needs to be large. That's how you make a fraction really big. Okay? So we've made Q as small as possible. The bare minimum is 2 needs to divide Q and 3 needs to divide Q. But if you're not satisfied with that, just say Q equals 6K. And then you'll have 363K divided by P is what you need to make an integer. And 286K divided by P is what needs to make an integer. And you'll find that P needs to be 11K, which we're going to do right now. Or rather, since we just said let Q be equal to 6, we're going to show that P needs to be 11. So now we need p to divide this and p to divide 363. Because once I plug in q equals 6 into the formulas over here, on the left side of these two, the q and the 6's, they sort of cancel out. So now what's left? Well, we need to make these integers. To make these integers, p, which is an integer, has to divide both of them. And we want p to be as large as possible. So we're just going to take p is the biggest common divisor here. Well, there's only two common divisors. So p is going to have to be 11. Let's write that out. 2 times 11 times 13. And p has to divide 3 times 11 squared. So it's not that hard to see. P divides 11. For p to be as big as possible, p is going to have to be equal to 11. So our squares are 11 by 6 times 11 by 6 centimeters. We get centimeters and centimeters here. Okay, so that's the size of our squares, but we're not asked for the size of our squares. Remember the question. What is the minimum number of squares required? Okay. Well, I've got my picture here. I've got 286. No, wait, sorry, this one's 286. 286 by 3, and I've got 363 by 2. And I'm going to have all these little squares fill up the whole area. And each one of them is 11 by 6. 11 by 6. So how many squares are over here? And how many squares are over here? Well, the first one will be how many 11 by 6's go into 286? By 3. So if we divide that by 11 by 6, we'll get 2 times 13. 2 times 11 times 13 over 3 times 6 by 11. Just invert and multiply. So the 11's cancel out, the 3 and the 6, so we should get 52. So there's 52 of our tiles along one side. 363 divided by 2 divided by 11 by 6. That's the same as 3 times 11 times 11. 6 over 11 divided by 2. 11's will cancel out. 2 and the 6 will give us a 3, so we'll have 3 times 11. That's 99. 99 times 52 is what? I have no idea. 99 times 52 is 5148. And so that should be the number of squares that we've got, right? 5148. That is one of our answers. Sure. But to me that seems kind of large. There's something I have mistaken here. I'm trying to think. It just seems like a really large number, all things considered. I'm just going to double check some calculations here. Okay, see, when I did 60.5 divided by 11 by 6, I get 33, not 99. So what have I done? I obviously have an extra factor of 3. Oh. These numbers should be over 6. Duh. I'm sure there was someone out there who was absolutely screaming at me about that. So these numbers will change. I was off. I was wondering, because 11 by 6 is that's just around 2. I shouldn't be getting 99 of them fitting in here. I should be getting something like 60 over 2, which would be 30. I was wondering what was up with that. Okay. Well, it's interesting to note that they put 5,148 in there, I assume, because they anticipated someone making a mistake like I just did. So 2 times 13, that should be 26. And you get a 6 here and a 6 here. The 11s and the 6s cancel out. We get the 33 that was originally predicted. So 33 times 26. So this is a nice example of where mental math had really helped me. So we get 858. I'll check whether or not that's in the list of possible answers in a moment. But it's always a good idea to sort of check, do the numbers you're getting make sense? And in that case, they weren't. Because remembering the original numbers, 60.5 is about 60, and 11 by 6 is a little sort of like 12 by 6, which is 2. I shouldn't be fitting 99 squares in here. Now I should be getting about 30. In fact, once I redid the calculation, I grabbed my calculator. I realized I had the wrong number representing 60.5. I got 33 squares fit in there. So, a little more confident now. 858. I like that. 858. That's B there. And just because I fumbled at the calculation there at the end, I'm just going to go through, verbally describe what I did again, double check, does this all make sense? Okay? And this is something that's important to do. If you've got the time, it's a good idea to do it. So, we did a little bit of investigation, but more importantly, over here on the right, we realized we needed n by n squares, and we actually gave a name to that side length. Okay. Converted these guys into fractions, and in fact, we went a little bit further, and we converted them into fractions with common denominators. And we explored it for a little bit and said, let n be m over 6, but I stopped for a moment and I said, as a mathematician, that doesn't seem right. I shouldn't be able to just jump to the denominator being 6. So I changed it and I said p over q. If you were fine with me saying n should be m over 6, you probably would have gotten 11 a lot faster. You probably did your calculations a lot smoother, and you didn't have that moment at the end where I might have circled the wrong answer. I almost said E instead of B. Okay? So I went back and I said, no, let's just make it a generic fraction, p and q. And we were able to deduce that q should probably be 6, or at least a multiple of 6, depending on how exact you want to be. And after that, we concluded that p's got to be 11. There's no bigger fraction for it to be. And then fumbled our calculations a little bit, but I'm much happier with this 26 and this 33. So, yeah, I like that a lot better. So I'm going to go with B. That's going to be my answer. And that's question number 24. We're going to look at the last question, question 25, in the next video. So thanks for watching.